Hello, everyone. As promised, I would like to share with you a walkthrough about how to get all the right answers on the in-class assignment for number 7. This says 9:30 at the top. The first page was the same for both sections. The last page was different, so I will switch over to the 11:30 version for the 11:30. I'm sorry, the 11 o'clock folk. Um, First, with the yes or no questions here. On number one, the presupposition that I laid down was that you have rejected the null hypothesis. That's the one thing that you know is true. What does it mean to reject the null hypothesis? Well, basically, if you're taking this as the model, then the fact that you rejected the null hypothesis means that you have gotten a result, your statistic for analysis has fallen on this side of the critical value. Whether or not you accept or reject the null has nothing to do with which distribution you're drawing from. It has to do with whether your answer was on one side or the other of the critical value. So you rejected the null hypothesis, which means that you're over here. Could you have made a type 2 error? Absolutely not. This red area represents type 2 error. That is the probability that you will fail to reject the null hypothesis if you're drawing from an alternative hypothesis curve. Since you didn't reject the null hypothesis, you couldn't possibly have made a type 2 error. Could you have made a type 1 error? Absolutely. If you got a result over here, but you were drawing from the null hypothesis curve, then you've made a type 1 error. So that's certainly possible. Okay, number two, you have failed to reject the null. That means that you are drawing a result from this side of the critical value. Could that have been a type 2 error? Yes, type 2 error exists on this side of the critical value. If you were drawing from the alternative hypothesis curve, then that result would have been a type 2 error. Could you have made a type 1 error? No. Type 1 error involves rejecting the null. If you fail to reject the null, then you can't possibly have made a type 1 error. Now, here's the number three, a different kind of a weird assumption that we don't usually get to make in real life, but I'm setting this up for educational purposes. Assume that the null hypothesis is in fact true, which means that you are drawing a result from this distribution right here, the one on the left. What is the probability that you'll make a type 2 error? None. It's impossible. You can't make a type 2 error no matter what you do if the null hypothesis is true, because type 2 error means failing to reject the null if the alternative is true. So if I've just told you that the alternative isn't true, you can't possibly make that error. What is the probability that you'll make a type 1 error? Well, that's what alpha is. If you are under the null hypothesis curve, there is an alpha probability that you'll reject the null anyway, um, and that's the green area. Alpha is determined before the fact. We're usually comfortable with a 5% probability of that happening. Assume that a specific alternative hypothesis is in fact true. What I'm telling you in number 4 is that we will be drawing a value from the alternative hypothesis curve here somewhere. What is the probability that you make a type 2 error? Beta is what that is. Beta is the probability that if you're drawing from an alternative hypothesis curve that you will nevertheless fail to reject the null. That's the definition of beta. The probability that you make a type 1 error, it can happen. If you reject the null under these circumstances, you've done the right thing. It's not an error at all. So a type 1 error means that you're drawing from the null hypothesis curve. Since you're not, you can't make a type 1 error. What's the probability that you'll reject the null hypothesis? That's power. That's 1 minus beta. So we're in this curve over here. I'm looking for the probability, which is the area under the curve, associated with being on this side of the critical value. That is 1 minus beta right there. Okay, number 6 and number 7, you decide to increase your alpha level from 0.01 to 0.05. What effect does this have on power? This will increase power. Take a look. Here is the line that is the critical value. That critical value is there because of the size of alpha. If I expanded alpha, if I made alpha bigger, if I made it push the critical error, it would push the critical value, it would push the critical value this way into the red. That would make the blue area bigger, which means that it would increase power. Group A runs an experiment and gets a standard error of 4.35. Group B runs the same experiment and gets identical results, except their standard error is 5.13. Which group will have more power? The smaller your standard error, the greater your power. the smaller standard error would mean that the same distance between these two peaks would now create greater separation between them if the error was smaller. All the null results would stick closely to mu sub null, and all the alternative results would stick closer to mu sub 1, which means that more of this curve, a greater proportion of this curve, would end up falling on this side of the critical value. Okay, at this point, we'll be moving on to page 2. And here's the setup. Do corner lots get more complaints per year from the homeowners association than other homes? If that is not the case, so what I'm doing here is I'm giving you all the possibilities that are not a part of the alternative hypothesis. If not, then the mu sub 1, the corner lot population, and mu sub 2, the overall population, would be less than. So mu sub 1 is less than or equal to mu sub 2. The other possibility, the alternative hypothesis, is that mu sub 2 is actually 5 complaints smaller than mu sub 1, which would mean corner lots get 5 more complaints than regular lots. So that if you took the mu of the corner lot population, subtracted the mu of the overall population, you would get 5. There's a difference of 5. Now, I have not needed in any way to give you the actual value of complaints for the first population or the second population, because that doesn't matter and it never has. The only thing that matters is whether those populations end up giving you the same value, in which subtracting one from the other will give you 0, or if they give you different values, which means subtracting one from the other will give you the treatment effect. So what I'm saying here is that the treatment effect, the effect of being a corner lot, is to get 5 more complaints. I've thrown you a standard error that is 2.25, and I've told you to assume that the sampling distributions are normal distributions. Now, this is a cheat here so that we can actually even do this thing. Because of course, you know that if we were actually running an independent samples t-test, we would take the number of people in the first sample, add it to the number of people in the second sample, and then subtract 2 to get degrees of freedom and start looking those values up in the t-table. The reason we can't do that is because the t-table isn't so finely grained that we can get a value for every point along the bottom axis. And so I've had to resort to using the z-table, which means throwing you the unfair assumption that these distributions are normal. But anyway, given that we've done that, I'm asking you to figure out a numerical value for power. That is to say 1 minus beta. So take a look at what we have here. 1 minus beta is this area right here. See the blue over here in the curve. The point that I want to make is that that blue area is made up of first half of the entire alternative hypothesis curve plus some chunk of the alternative hypothesis curve that is between the critical value and the mean. This chunk is the one that's mysterious. We know that this is a half, but we don't know what this one is. So what we need to do is find that area. The way to find an area off of a z-table is to get the number of standard deviations that separate the border of that area from the middle. So that's a chunk that is perfectly reasonable to look up in the z-table. But we don't know how many standard errors this is, that is to say how many standard deviations, so we've got to figure that out. And the way we figure that out is to figure out how many standard errors are between the middle of these two distributions, then figure out how many standard errors are right here, subtract this value from this value to get the value we need to look up on the z-table to get an area for right here. Add it to 0.5 and get our answer. So here's how it happened. I was trying to get you to make this a one-tailed test by making the prediction directional, but if you went with the two-tailed test, I can't really blame you, so I have answers here for both of them. The thing is, the number of standard errors that separate the middle of the null distribution from the mu you'd get if the research hypothesis was true, this treatment effect here is treatment effect divided by standard error. In this case, 5 complaints separate these two distributions. One standard error is 2.25, so you put 5 over 2.25 and you get the answer that the middle of this distribution to the middle of this distribution is 2.22 repeating standard errors, not complaints, but standard errors. All right. How many standard errors away from the middle of the null distribution is the critical value? Well, this is something that you don't need the treatment effect for. You don't need the alternative hypothesis for. The number of standard errors out you have to go to reach the critical value is determined completely by what is going on in your null distribution and the alpha that you have chosen. So if you did a one-tailed test, you could look up the z-table area for 0.4500. That would be half the curve here minus the alpha 0.05 that is not included. And you realize that if the area here is 45%, then the distance between here and here, that's the number of standard errors you looked up on the z-table, would be equal to 1.65. If you decided to do a two-tailed test, well, that's an old friend right here. This is one we've seen a lot before. A two-tailed test gives you a z-value of 1.96 standard errors in either direction. So under a one-tailed assumption, this is 1.65, and let's just follow that through to the end. Under the one-tailed assumption then, 2.2222 standard errors minus 1.65 standard errors gives you 0.57 standard errors right here between the middle and the critical value. Then what we have to do is take that 0.57 to the z-table and figure out how much area is covered by going 0.57 of one standard error away from the middle of a normal distribution. That is, if you look up 0.57 in the z-table, that is 0.2157 of the entire curve. So this thing right here is 0.2157 of that normal curve. If you add that to the other half of the curve, then you get 0.7157. That makes up power here. That would be the actual value. See, the blue area over here, 1 minus beta, this one minus beta, 0.7157. Now, since it's a proportion, if you want to put it in significant figures, you should use 3 decimals, 0.716. Now, just to go back and for completion's sake, do it two-tailed. If 1.96 was your value for the critical value, then this distance here is 1.96, so 2.22, the entire distance for the treatment effect, minus 1.96 standard errors is 0.262 standard errors right here between this point and this point. If you looked up 0.26 in the z-table, you would see that it is 0.1026. So this area right here is 0.1026. If you add that to 0.5, you get 0.6026. So this area here is 0.603 if you did a two-tailed. Notice, just for your edification, that by giving yourself the advantage of doing a one-tailed test, you've increased power. You've increased the probability of finding an effect. Interesting to note. So that's how you do the 9:30 version of the in-class assignment 7. I will be back with you again tomorrow night, that is to say Tuesday morning, for coverage of the next chapter.